Hello students, welcome back. Let's have an easy topic for a change. Lesson 2b, first order linear equations. A linear equation is an equation that looks like this. This is the general form. Please pay attention to all the y's. Y, y prime, y double prime, and so on, all the way over to the nth derivative. They all have degree 1. No square, no cube, no radical, no transcendental, no nothing. They're all linear. This kind of equation is called a linear ODE. Now, the other part, f of t, or the coefficient functions, a0 of t, a1 of t, and so on, they can be nonlinear. That doesn't matter. As long as all the y's are linear, we are going to call it a linear ODE. Now, this is the nth order linear ODE, so the leading coefficient should not be 0. Otherwise, it's not going to be nth order anymore. So you can divide by this an of t and solve for the nth derivative, and you're going to get this form. This is the standard form that we are going to work with, at least for this lesson. Okay, let's go. Here is the first order linear ODE in the standard form. Please note that the leading coefficient is 1, so we already divided and made it into standard. Here, we're going to use the method of integrating factor, and so-called the integrating factor is defined like this. Mu of t is defined as exponential of the antiderivative of p of t, like this. I need bigger font, even bigger. So take the antiderivative of this first coefficient function and take the exponential of that antiderivative. And that's the integrating factor. Now, calculating this with this notation is going to be really messy. And if you try to write it and do a couple of lines, you'll see. We have exponential and then this big integral as a power, and it's messy. So I'd much prefer to write the same thing like this, e to the q power, where q is the antiderivative. Oh, excuse me, I forgot prime. I'd much rather do it this way. Now, some textbook authors use capital P here instead of capital Q, but I don't like it because small p versus large p, it's really difficult to distinguish one another, and especially in handwriting, it's nearly impossible, especially if I write quickly. So I don't do that. I'd prefer to use capital Q for the antiderivative. So that's the notation issue. And once you multiply that, once you have that integrating factor, e to the q power, what I'm going to do next is to multiply this to both sides of the original standard form of the equation and distribute it around like this. Can I do this? Yes, I can. I can always multiply any non-zero number to any equation and distribute around. And exponential is never 0, so it's okay. But does it improve this equation? Yes, it does. The left-hand side here becomes this. And what did I end up with? We had 2 terms, but the derivative only 1 term, and this is a big improvement. Let's check if this is really true. Let's increase the font a little bit. And let's calculate this derivative using the product rule. You see, you have y of t times this exponential, so it's going to be a product rule. So derivative of the first function times the second function plus first function times the derivative of the second function. Now, derivative of exponential always stays the same. And by chain rule, you have to multiply the derivative of the inside. But what's q prime? q prime is p. So let's replace this one by p of t, and what do we have? This right-hand side here is exactly the same as this original. So what did it prove? This highlighted part and that highlighted part are the same. In short, by multiplying the integrating factor to both left-hand side and right-hand side, we were able to simplify left-hand side into this single derivative. This is a huge simplification because all you have to do now is to take the antiderivative and then divide away this integrating factor to the other side, and voila, we have the answer. Now you can work it out as a formula and start from here, and I'm not going to stop you from doing that, no deduction or anything like that, but still I don't recommend it. There are many other integrating factors out there and methods are similar, but of course we have different circumstances, so formulas are all different. So if you memorize all these formulas and then try to do it with formula method, soon you're going to be swimming in other dozen different formulas and there's no apparent connection and it's going to be a mess. So I do not recommend it. What I do recommend is to go through this method of integrating factor and try to master it. Once you do, then you can use the same method with a bit of variation to all kind of different integrating factors as well. And they're going to look all easy to you once you master one. But if you rely upon the formula, then, well, your knowledge will be really hazy. I do not recommend it. So let's begin. And we're going to be following through that method of integrating factor. So t squared y prime plus ty equals to 1 is the problem. And the very first step is always to make it a standard form. Y prime plus dividing by t squared, 1 over ty equals 1 over t squared, dividing by t squared. Alright, this is in the standard form now. So we have y prime plus py equals to f. So what's p? Here, 1 over t. So let's get the integrating factor. Q is antiderivative of p. So it is antiderivative of 1 over t, which is log of t. Therefore, the integrating factor is exponential of log of t, which is just t. Alright, the integrating factor became really easy. And now I'm going to multiply this to each term in the standard form. What do you get? T y prime plus y equals to 1 over t. Did I do this right? Okay, now let's combine the left-hand side into a single derivative. T times y, and then right-hand side is 1 over t, of course. By the way, experienced students will skip this step and go to this directly. Why? Let's go back to this derivation in general. And what was the purpose of all this business? The very purpose of this method of integrating factor was to get this left-hand side as a single derivative. Derivative of y times that integrating factor. That's where we're headed. So that's not something you should be forgetting it. So derivative of integrating factor times y, next time you're going to go directly to that. Alright, we have the derivative on my left hand side, so let's take the antiderivative. T times y is equal to the antiderivative of 1 over t. And what is this antiderivative? It's log of t, isn't it? And then we need plus c here. Let's go to the answer. Let's divide away this integrating factor. So we have 1 over t times log of t plus c. And there goes the answer. Shall you check? Okay. Y of t is 1 over t c plus log of t. And then simplify this equation. T squared y prime of t plus t times y of t, and then minus 1. Subtract the right hand side. Yes, we have 0. If the right hand side is simple, you can do that as well and see if you get the right hand side. But usually, I prefer to subtract the right hand side into left and then compare it with 0. That's more effective, especially when you have something more complicated in the right hand side. A comment here. In this anti-differentiation, I did not need plus c. Here, I do. Why not? Because I'm looking for any integrating factor. Whether I select my q as log of t, or log of t plus 5, or log of t minus square root of 17, it does not matter. As long as q is an antiderivative of p, this integrating factor will work out just fine. So why do I make it more complicated? It's counterproductive. So we don't need it. You see, here, after all, we are taking the derivative, so that plus c there will not contribute at all. But down here it does, because this is integral constant, which is the undetermined constant that will be determined from initial condition if there's any. So we do need it. The first integral, no c. If there are more integrals in between, no c, no, no, no. The very last one, yes you do. Okay, how about the next problem? Okay, is this in a standard form? Almost. I don't have leading coefficient here, so I don't have to divide anything, but I'll have to flip this one over to the other side. So y prime minus tangent of t, y is equal to cosine of t. That's the standard form. Let's find the antiderivative of this, and then let's find the integrating factor, okay? Integral of tangent of t. And what's the antiderivative of tangent? Does everybody recall? It is, does everybody recall? Maybe you can stop this playback and then go to the integral table and check it out. What is it? It turns out to be log of secant. So integrating factor is e to the q power, so it's e to the log of secant. So it's secant of t. Okay, whenever you have logarithm in this integrating factor computation, I'm happy because that'll kill off this exponential. All right, let's go to the standard form of the equation here and multiply the integrating factor to each term and simplify. But this time, I'll take the clever approach. The derivative of integrating factor times y. And then we are multiplying the integrating factor, right? Cosine times secant. What is cosine times secant? Secant is 1 over cosine, isn't it? So this whole thing becomes 1. Very simple. Oh, looking good. So y times secant of t is equal to the antiderivative of just 1. So this is t plus c. I'm almost there. Divide by secant, and I'm going to get But nobody writes like this. What is secant? Secant is 1 over cosine, so it should be written as y equal to t plus c cosine of t. Oops. Does it look good? Is everybody happy? Okay, let's check. So t plus c cosine of t, and then let's simplify this. Y prime of t, and subtract the right hand side. Tangent of t times y of t minus cosine of t, and simplify. Am I gonna get 0? Uh-oh, something is wrong. Obviously, there was a mistake. Where is it? Your job is to find out this mistake and correct it. Maybe it's a good idea to stop this recording, stop this playback, and find out the mistake and correct it, and then resume. Well, did everybody find mistake? Where is it? It's right here. Right here. This is incorrect. You see, Q is antiderivative of P of t, right? What is P of t in this particular case? It's negative tangent of t. You see, this negative sign is part of the next term. So this tangent here is wrong. I need negative tangent. So all these computations from here all the way to the end, they're all wrong, and you have to get it right. So how do you calculate it? Negative sine of t over cosine of t. And then you can calculate it throughout the integration by substitution. Derivative of cosine is negative sine, so it'll turn out this is log of cosine. Not log of secant, log of cosine. So the integrating factor is e to the q, so e to the log of cosine, and that is cosine of t, not secant, it's cosine. So all these are wrong, so let's do this in the right way. Y times the integrating factor is, now I have to multiply by integrating factor, so this is cosine squared. Take the antiderivative, y cosine of t is equal to the integral of cosine squared. How do you do this integral? This is something you must have done time and time again in calculus 2. What formula do you use? Oops, I'm forgetting t here. Double angle formula, half angle formula, or power reduction formula. It has many names. That's what we use. If it is sine squared, this will become negative. So what do you get? You have 1/2 t plus 1/4 sine of 2t. So what's the final answer? Y equals 2 divided by cosine, so secant of t times this. And that's the final answer. Checking this final answer is left to the students. Let's stop here.